Welcome back, everyone, to another deep dive on the Explainer. Today, we're unpacking a truly fascinating event that just wrapped up at the University of Pennsylvania. It's the 4th Conference on Lifelong Learning Agents, or CoLLAs 2025. Now, if you follow AI, you already know this field moves at lightning speed, but this specific conference, it hones in on an absolutely critical frontier. We're not just talking about making models bigger anymore, we're talking about fundamentally changing how they learn and retain information over time.
So the big question is, can an AI learn continuously without just forgetting the past? It sounds simple, right? I mean, you and I learn new things every single day, and we don't suddenly forget how to ride a bike or speak our native language. But for artificial intelligence, this is an absolutely massive, almost existential hurdle. When standard AI models learn new data, they tend to aggressively overwrite their previous knowledge. So setting the stakes for our explainer today, the holy grail of this entire field of research is creating agents that can learn continuously across their entire lifespan, exactly like we do.
Okay, let's dive into this and map out our 5 distinct tracks from the conference proceedings. 1. The lifelong learning revolution. 2. Solving catastrophic forgetting. 3. Real-world agents and robotics. 4. Scaling continual learning. And 5. Radical new AI paradigms.
Let's kick things off with Track 1, the lifelong learning revolution.
Looking directly at the research presented at CoLLAs, continual learning is defined as the ability of an agent to adapt to first session or ongoing data without needing time-based embodiment resets. Now, what does that actually mean in plain everyday terms? Well, imagine you've got a smart robot operating in your home. You definitely don't want to turn it off, wipe its memory, and completely retrain its software every single time you buy a new couch or rearrange your living room. It needs to adapt on the fly, right? It has to deal with continuous streaming data without relying on a full system reboot. Basically, it has to learn while doing, which is exactly the baseline these researchers are trying to achieve.
Moving right along to Track 2, solving catastrophic forgetting.
Getting an AI to learn continually without totally breaking down brings us to the biggest battle in this field. Researchers like Ashraf Jaziri and his colleagues point out that the fundamental roadblock here is something called the stability-plasticity dilemma. Think of it as the intense challenge of balancing a model's ability to retain old knowledge, that's the stability part, while remaining highly adaptable to new incoming data, which is the plasticity. If you design an AI that leans too far toward stability, it gets rigid. It literally can't learn anything new. But if it leans too far toward plasticity, you get what experts call catastrophic forgetting. The new information violently overwrites the old, leaving the AI completely oblivious to what it knew just yesterday.
It's basically a massive tug of war. Stability on one side, trying to hold on to the past, and plasticity on the other, eager to absorb the future. The proceedings at CoLLAs 2025 showcased researchers attacking this delicate balance from multiple, really fascinating angles. For instance, some teams are experimenting with a technique called adaptive linearity injection, which cleverly tries to preserve that plasticity as the network grows. Others are digging deep into the foundational architecture of neural networks. There's a really robust debate right now about whether it's better to reinitialize the network's weights or just reset the units entirely, all to maintain this equilibrium when the AI encounters fresh information.
Now, what's really interesting about this next finding is that it totally flips conventional wisdom on its head. Researcher Yaseman Mahadavia and her team came out with a massive revelation. Replay can provably increase forgetting. This is huge. In the AI industry, replay, which basically means making the AI practice old data alongside new data, has been the standard go-to fix for catastrophic forgetting for years. It's like using flashcards. Yet this paper proves mathematically that under certain conditions, forcing a model to replay past memories can actually accelerate the forgetting process. It's a highly counterintuitive finding, and it's forcing the whole field to rethink its standard toolkit.
So, if standard replay is flawed, how on earth do we fix this forgetting problem? Well, the conference presented a pretty diverse array of highly technical solutions. For example, teams are proposing methods like curriculum-driven continual DQN expansion. Think of this almost like giving the AI a structured school syllabus, feeding it easier tasks before harder ones to make the new information more digestible. Then you have data-driven weight initialization, ensuring the AI starts off with a strong, optimized foundational state before the learning even begins. And honestly, even variations of replay are getting massive upgrades, like replay consolidation with label propagation for really complex tasks like object detection. The big takeaway here? We absolutely need smarter, more targeted memory fixes, not just brute force repetition. Let's shift gears to track 3, real-world agents and robotics.
Now we get to move from all that deep theory into how this actually looks in the physical world. This is where cutting-edge theory meets reality. In mobile devices, researchers are benchmarking control agents across diverse configurations to see how well an AI can navigate different operating systems over time without breaking down. Moving down to single-life robots, this is super fascinating. These are agents deployed in the real world that have to adapt on the go through behavior modulation. They don't have a safe little simulation to practice in, they literally get one shot at the task. And finally, in embodied AI, there's groundbreaking work on semantics-aware conversation, which helps lifelong robots chat and interact safely with humans even when they bump into concepts they are completely unaware of.
You have to check out this specific framework developed by Yanla Yang and Mengyi Ren, called the Memory Storyboard. Their paper looks at how agents process continuous streams of visual data. By leveraging something called temporal segmentation, the AI basically chunks streaming first-person video, like from a camera mounted on a robot's head, into a self-supervised storyboard. It's a brilliant way to help an agent understand and remember continuous events over time. Actually, it essentially mimics how we humans organize our own memories into distinct sequential events, rather than just one blurry, endless video feed in our heads.
All right, track 4, scaling continual learning. Let's move to and see how this builds, because of course the elephant in every AI research room right now is scale. Everything just needs to be bigger and faster. The research presented here shows a clear, step-by-step evolution in how we handle massive systems. Step 1 focuses on the continual pre-training of models, trying to bake adaptability into the core foundation right from the beginning, rather than just slapping it on as an afterthought. Step 2 looks at retrieval-augmented decision transformers. That's essentially giving reinforcement learning agents an external, highly organized memory bank they can query in real time when making decisions. And Step 3 highlights a huge push for efficiency, specifically through methods like CoLLA, which stands for Parameter-Efficient Continual Learning with Low-Rank Adaptation. This is vital, folks, because it proves we can continuously update massive AI models without needing a multi-million-dollar supercomputer every single time we run an update.
When we apply these scaling concepts directly to large language models, the breakthroughs are incredibly exciting. Researchers are actively revisiting gradient alignment for the continual pre-training of LLMs, forcing these text models to get smarter over time without losing their initial grammar or logic. There's also a major push for zeroth-order federated pre-training. I know, it's a mouthful, but it essentially means allowing low-resource clients, like your personal laptop or your smartphone, to help train these models collaboratively on the edge without having to share your private, local data with some central server. And crucially, we're seeing continual learning applied to multimodal large language models. We are building AI that can continuously learn from text, images, and audio simultaneously, without the whole memory system collapsing.
And finally, track 5, radical new AI paradigms. Which leads us perfectly into our final and perhaps most mind-bending section. What can grokking teach us about learning under non-stationarity? That is the exact title of a brilliant paper by Claire Lyle and her colleagues. If you haven't heard of it, grokking is this highly mysterious phenomenon in AI where a model suddenly just gets a concept. It generalizes perfectly after a long period of seemingly failing to learn it at all. It's like a delayed light bulb moment. By questioning how this spark of understanding happens in non-stationary or constantly changing environments, these researchers are probing the absolute deepest foundational behaviors of how neural networks process and store understanding over long periods. So, the crucial point is, if you want a truly radical paradigm shift, consider this paper. No prop, training neural networks without backpropagation or forward propagation. To really grasp why this is crazy, you have to know that backpropagation is literally the bedrock of how modern AI learns. It is the core math of how errors are calculated and fixed in almost every single model today. So, researchers like Kyunyu Lee, Yi Wai-Te, and Razvan Pascanu are daring to rethink neural network training entirely from scratch, literally throwing out the standard playbook. It's disruptive, highly ambitious ideas like this that remind us the current way we build AI is almost certainly not the final way. As we wrap up this explainer on the cutting-edge insights from CoLLAs 2025, I want to leave you with a provocative question to chew on. What will AI learn next? We've seen today that the journey from models that catastrophically forget to true, lifelong learning agents is filled with massive hurdles. From navigating the stability-plasticity dilemma to rethinking mathematical foundations to managing incredible computing costs. But the research from the University of Pennsylvania proves that bold, wild solutions are arriving fast. If researchers can solve this memory problem, we don't just get slightly better software, we get AI that evolves, adapts, and grows alongside us, continuously for a lifetime. Thanks so much for joining me on this deep dive. Keep asking questions, keep learning, and I'll catch you in the next explainer.